Hello friends, welcome to the course on differential calculus. In this session, the concept of tangent line to a curve at a point will be described by observing the behavior of the secant through that point. The average rate of change of a function over an interval and the instantaneous rate of change of a function at a particular point will be discussed. We will also describe rectilinear motion, position versus time curve and velocity of a moving particle, secant line, tangent line and chord to a circle. A straight line can be intersect a circle in 2, 1 or 0 point. A line intersecting a circle in 2 points is called a secant line, exactly at one point a tangent line and in no point an exterior line. In case of tangent line, the unique point on the circle where the tangent line meets is called the point of tangency. A chord of a circle is the line segment that join two distinct points of the circle. A chord is therefore contained in a unique secant line and each secant line determines a unique chord. What is tangent to a curve? Now let us try to answer the question. What is tangent to a curve? We have seen that for circle, tangency is straightforward. That is, a line is a tangent to a circle if it meets the circle at precisely one point. In figure 2, the line L is tangent to a circle at a point P. From figure, we observe that if L is a tangent to the circle C, then first one, L passes through P and is perpendicular to the line from P to the center of the circle C. Second one, L passes through only one point of C, namely P. Third one, L passes through P and lies on one side of C only. While these statements are valid if C is a circle, none of them work consistently for more general curves. Most curves do not have centers and a line we may want to call tangent may intersect C at other points or cross C at the point of tangency. For example, in the curve in figure 3, the line L meets the curve C only at the point P but is not tangent to C. But for the curve in figure 4, the line L is tangent to the curve C at the point P but meets C at several points. For the curve in figure 5, the line L is tangent to C at P but lies on two sides of the curve C, crossing C at P. The observations above shows that the definition of tangent to a circle is not appropriate for more general curves. To obtain a definition of a tangent line that applies to curves other than circle, we must view tangent lines another way. Suppose that we are interested in the tangent line at a point P on a curve C in the xy plane and that Q is any point that lies on the curve and is different from P. The line through P and Q is called a secant line for the curve at P. We note that a secant line of a curve is a line that intersects the curve in at least two distinct points. In the case of a circle, a secant line will intersect the circle in exactly 2 points, but for a general curve, it may touch more than 2 points. Intuition suggests that if we move the point Q along the curve towards P, then the secant line will rotate towards a limiting position. The line in this limiting position is what we will consider to be the tangent line at P. This new concept of tangent line coincides with the traditional concept when applied to circles. To define tangency at a point P, we need a dynamic approach that takes into account the behavior of the secant through P and nearby points Q, and Q moves towards P along the curve. It goes like this. First one, we start with what we can calculate, namely the slope of the secant PQ. For the secant line PQ to the curve y equal to f of x, where P is ordered pair x0 f of x0 and Q is ordered pair x1 f of x1. The slope of the secant line PQ to the curve y equal to f of x is given by m secant equal to f of x1 minus f of x0 upon x1 minus x0. The ratio f of x1 minus f of x0 upon x1 minus x0 is called a difference quotient. Second one, investigate the limit of the secant slope as q approaches p along the curve. That is, we examine whether the limit of f of x1 minus f of x0 upon x1 minus x0 as x1 approach x0 exists or not. Third one, if the limit exists, take into the slope of the curve at p given by m curve equal to limit of f of x1 minus f of x0 upon x1 minus x0 as x1 approaches to x0. Also define the tangent line or simply tangent to the curve at p to be the line through p with this slope. We remark that the tangent line to a plane curve at a given point is the straight line that just touches the curve at that point. As the tangent line passes to the point where it meets the curve, that is through the point of tangency, and the tangent line is going to the same direction as the curve. It is the best straight line approximation to the curve at that point. As an example, consider the function f of x equal to 4x plus x square and the point p ordered pair 1 f of 1 equal to ordered pair 1 5. First we find the slope of secant line to the graph of y equal to f of x determined by p and points on the graph at x equal to 1.5 and x equal to 3. The secant line to the graph f through p and the q of ordered pair 1.5 f of 1.5 equal to ordered pair 1.5 8.25 has slope m secant equal to 8.25 minus 5 upon 1.5 minus 1 equal to 6.5. The secant line to the graph of f through p and q of ordered pair 3 f of 3 equal to ordered pair 3 21 has slope m secant equal to 21 minus 5 upon 3 minus 1 equal to 8. Next we find the slope of the graph of y equal to f of x equal to 4x plus x square and the point p of 1 f of 1 equal to ordered pair 1 5. The slope of the graph of f at the point p with x naught equal to 1 is m curve equal to limit of f of x1 minus f of 1 upon x1 minus 1 as x1 approaches to 1 equal to limit of 4x1 plus x1 square minus 5 upon x1 minus 1 as x1 approaches to 1. Here the limit of the numerator and the denominator are 0, which is equal to limit of x1 plus 5 into x1 minus 1 upon x1 minus 1 as x1 approaches 1 by identifying common factors, which is equal to limit of x1 plus 5 as x1 approaches 1 by cancelling common factors, which is equal to 6. We now show that the line y equal to mx plus b is its own tangent at any point p of x naught f of x naught equal to ordered pair x naught mx naught plus b. Letting f of x equal to mx plus b, we have m curve at the point p of x naught f of x naught is m curve equal to limit of f of x1 minus f of x naught upon x1 minus x naught as x1 approaches x naught, which is equal to limit of mx1 plus b minus mx naught plus b upon x1 minus x naught as x1 approaches x naught, which is equal to limit of m times x1 minus x naught upon x1 minus x naught as x1 approaches to x naught, which is equal to limit of m as x1 approaches x naught by cancelling common factors, which is equal to m by cancelling common factors. Now using the point slope of the equation of a line having slope m and passing through ordered pair x naught y naught given by y minus y naught equal to m times x minus x naught. We obtain the equation of tangent line at a point ordered pair x mx naught plus b as follows: y minus mx naught plus b equal to m times x minus x naught, that is y equal to mx plus b on simplification. Hence, the line y equal to mx plus b is its own tangent at any point p of ordered pair x naught f of x naught equal to ordered pair x naught mx naught plus b. As another example, we find the slope of the curve y equal to 1 upon x at x equal to a as follows with x naught equal to a. M curve equal to limit of f of x1 minus f of a upon x1 minus a as x1 approaches to a, which is equal to limit of 1 upon x1 minus 1 upon a upon x1 minus a as x1 approaches to a, which is equal to limit of a minus x1 upon a x1 upon x1 minus a as x approaches a, which is equal to limit of negative 1 upon a x1 as x1 approaches to a, cancelling common factors x1 minus a, which is equal to negative 1 upon a square by substituting x1 equal to a. Note that the slope of negative 1 upon a square is always negative. Now, let us find where does the slope equal negative 1 upon 4. If the slope of the curve y equal to 1 upon x at a point x equal to a is negative 1 upon 4, then negative 1 upon a square equal to negative 1 upon 4. This equation is equivalent to a square equal to 4. So, a equal to 2 or a equal to negative 2. It follows that the curve has slope negative 1 upon 4 at the 2 points ordered pair 2 1 upon 2 and ordered pair negative 2 negative 1 upon 2. Let us see that what happens to the tangent to the curve at the point ordered pair a 1 upon a as a changes. Since the slope negative a upon a square is always negative, as a approaches 0 from the right, the slope approaches negative infinity and the tangent become increasingly steep. We see this equation as a approaches 0 from the left, as a moves away from the origin, the slope approaches 0 and the tangent become flat and parallel to the x axis. Rates of change. If y equal to f of x, then the average rate of change of y with respect to x over the interval closed interval x0 x1 is R average equal to f of x1 minus f of x0 upon x1 minus x0, and the instantaneous rate of change of y with respect to x when x equal to x0 is R instantaneous equal to limit of f of x1 minus f of x0 upon x1 minus x0 as x1 approaches to x0. For the curve y equal to 1 upon x, we first find the average rate of change of y with respect to x over the interval closed interval 2 3 with f of x equal to 1 upon x, x0 equal to 2 and x1 equal to 3. Our average equal to f of x1 minus f of x0 upon x1 minus x0, which is equal to f of 3 minus f of 2 upon 3 minus 2, which is equal to 1 upon 3 minus 1 upon 2 upon 1 equal to negative 1 upon 6. Thus, on the average y decreases negative 1 upon 6 units per unit increase in x over the interval closed interval 2 3. Secondly, for the curve y equal to 1 upon x, we find the instantaneous rate of y with respect to x when x equal to 2 with f of x equal to 1 upon x and x not equal to 2. Our instantaneous equal to limit of f of x1 minus f of x0 upon x1 minus x0 as x1 approaches to x0, which is equal to limit of f of x1 minus f of 2 upon x1 minus 2 as x1 approaches to 2, which is equal to limit of 1 upon x1 minus 1 upon 2 upon x1 minus 2 as x1 approaches to 2, which is equal to limit of 2 minus x1 upon 2x1 upon x1 minus 2 as x1 approaches to 2, which is equal to limit of negative 1 upon 2x1 as x1 approaches to 2, which is equal to negative 1 upon 4. Thus, for a small change in x from x equal to 2, the value of y will change approximately 1 upon 4 times as much in the opposite direction. That is, because the instantaneous rate of change is negative, the value of y decreases as value of x move through x equal to 2 from left to right. Finally, for the curve y equal to 1 upon x, we find the instantaneous rate of change of y with respect to x at the general point corresponding to x equal to x naught. That is, R instantaneous equal to limit of f of x1 minus f of x naught upon x1 minus x naught as x1 approaches to x naught equal to limit of 1 upon x1 minus 1 upon x naught upon x1 minus x naught as x1 approaches to x naught equal to limit of x naught minus x1 upon x1 x naught upon x1 minus x naught as x1 approaches to x0, which is equal to limit of negative 1 upon x1 x0 as x1 approaches to x0 equal to negative 1 upon x0 square. Thus, the instantaneous rate of change of y with respect to x at x equal to x0 is negative 1 upon x0 square. In particular, setting x0 equal to 2, the instantaneous rate of change of y with respect to x when x equal to x0 equal to 2 is r instantaneous equal to negative 1 upon 4. We remarked that in applied problems, average and instantaneous rate of change must be accompanied by appropriate units. In general, the units for a rate of change of y with respect to x are obtained by dividing the unit of y by the unit of x and then simplifying according to the standard rules of algebra. For example, if y in meters and x in second, then the rate of change of y with respect to x has unit of meter per second. As another example, if y is in Newton meter and x is in meter, then a rate of change of y with respect to x has unit of Newton, since Newton meter per meter equal to Newton. With the discussion so far, let us reconsider the problem discussed in this session, limit and intuitive approach. Suppose a car is driven such that after t second was 0 less than or equal to t less than or equal to 12, it is s of t equal to 1.5 t square meters from its initial position. That is, the distance covered after t second is given by s of t equal to 1.5 t square meter, 0 less than or equal to t less than or equal to 12. If 0 less than or equal to t naught strictly less than t1 less than or equal to 12, the average speed over an interval closed interval t naught t1, that is the rate of change of distance with respect to time over the interval closed interval x naught x1 is r average equal to s of t1 minus s of t naught upon t1 minus t naught, which is equal to 1.5 t1 square minus 1.5 t naught square upon t1 minus t naught, which is equal to 1.5 times t1 plus t naught by algebraic simplification. The instantaneous speed at a time t equal to t naught is r instantaneous equal to limit of s of t1 minus s of t naught upon t1 minus t naught as t1 approaches to t naught, which is equal to limit of 1.5 times t1 plus t naught as t1 approaches to t naught, which is equal to 1.5 times 2 t naught, which is equal to 3 t naught. In particular, the instantaneous speed at a time t equal to 6 is 3 times 6 equal to 18. This justifies the observation in this session, limits and intuitive approach. Geometrically, if we draw a graph of the curve s of t equal to 1.5 t square, 0 less than or equal to t less than or equal to 12 in an st coordinate plane, then the slope of the tangent to the curve when t equal to 6, that is at the point ordered by a 6, 54 is 2. Velocity. One of the important themes in calculus is the study of motion. Just now we have considered an example involving speed and average speed of a moving particle. To describe the motion of an object completely, speed, how fast it is going is not enough. We have to take into consideration the direction in which the object is moving. The speed and the direction of motion together comprise what is called the velocity of the object. For example, knowing that the speed of a train is 150 km per hour tells us how fast it is going, but not which the way it is moving. In contrast, knowing the velocity of a train is 900 km per hour due north gives the speed and the direction of motion. In real life, we have to consider motion of objects in 2 or 3 dimensional space. But for now, we will consider motion along a line. This is called rectilinear motion. Some examples are motion of an object dropped from the top of a building and falling straight down, a piston moving up and down in a cylinder, and a train moving along a straight track for computational purpose. We assume that a particle is allowed to move in either direction along a coordinate line. The coordinate line might be an x axis, a y axis or an axis that is inclined at some angle. To avoid being specific, sometimes coordinate line is denoted as s-axis. As the particle moves along the s-axis, its position coordinate is some function s equal to f of t of the elapsed time t from starting time t equal to 0. We call f the position function of the particle and we call the graph of s versus t the position versus time curve. Position versus time curve of rectilinear motion of a car. If a car starts from the origin and moves only in the positive direction of its axis, then its position versus time curve will be like in the one in figure. Position versus time curve of motion of a ball thrown up. In rectilinear motion, the average velocity of a particle over a time interval closed interval t naught t1 is V average equal to change in position upon time elapsed, which is equal to f of t1 minus f of t naught upon t1 minus t naught. If t1 equal to t naught plus h were h greater than 0, then the average velocity of the particle over a time interval closed interval t naught plus h is V average equal to f of t naught plus h minus f of t naught upon h. We define the instantaneous velocity V instant of a particle at a time t naught to be the limit as h approaches 0 of its average velocity V average over the time interval closed interval t naught plus h and is given by V instantaneous equal to limit of f of t naught plus h minus f of t naught upon h as h approaches 0. As an example, suppose a ball is thrown vertically upward so that the height in feet of the ball above the ground t second after its release modeled by the function s of t equal to negative 16 t square plus 29 t plus 6 was 0 less than or equal to t less than or equal to 2. The position versus time curve of the displacement function s of t, which mathematically describe the rectilinear motion of the ball, is given in figure. We observe at the initial time, that is when t equal to 0, the ball is at a height 6 feet above the ground. The ball is thrown straight up in the positive direction of the s axis from the height 6 feet and then falls straight down in a negative direction. We determine the instantaneous velocity of the ball at a time t equal to 0.5 as follows. V instantaneous equal to limit of f of 0.5 plus h minus f of 0.5 upon h as h approaches 0, which is equal to limit of negative 16 times 0.5 plus h whole square plus 29 times 0.5 plus h plus 0.5 minus 11 upon h as h approaches 0, which is equal to limit of negative 16 h square plus 13 h upon h as h approaches 0, which is equal to limit of negative 16 h plus 13 as h approaches 0, which is equal to 13. That is, the instantaneous velocity of the ball at a time t equal to 0.5 second is 13 feet per second. Let us summarize the session. In this session, the concept of tangent line to a curve at a point is described and illustrated through example. The average rate of change of function over an interval and the instantaneous rate of change of the function at a particular point are discussed. We also describe rectilinear motion, position versus time curve and velocity of a moving particle.